13 in an introductory class in electricity and magnetism. And in this lecture, I'm going to talk about the relationship between what is called the scalar potential, or the electric potential, and the electric field. So the field in particular is the electric field. So there are a couple of learning outcomes for this lecture. The first one is to be able to use the relationship between the field and potential to determine information about one given information about the other. And the other learning outcome is to determine the equipotential surfaces from a field line diagram. I guess that's an okay way to put that. So in order to show you stuff for these learning outcomes, I'm going to show you, I'm going to describe the relationship between the field and the potential, Actually, I'm going to start off by describing the mathematical relationship between field and potential. So it's kind of like we should be able to go from, for example, if we're given the potential, we should be able to, these are supposed to be little arrows, give the field. But also, if we're given the field, we should be able to give the potential. So sort of both directions. That's real clumsy use of the typing. So anyhow, so after this is going to be mathy. It's going to feel mathy. But while I show you this mathematical relationship, we're going to also explore it a little bit, and we'll be able to take away, just because of the explorations, a reasoning for why they're, say, on a field line diagram, how could you also diagram something about the scalar potential? And you'll learn about this, the reason why these diagrams make sense while we do some calculus up here, because the relationship between the scalar potential V and the electric field E is a calculus relationship. Right, so actually, maybe in here, I'm going to add another, actually not a bullet point, but just another line. This is the fundamental theorem of calculus. Basically, the integral of the derivative of a function is the function up to a constant. Right, that's a way to say in English what the fundamental theorem of calculus is. All right. So in a nutshell, the relationship between the scalar potential and the electric field is essentially the fundamental theorem of calculus. So let me write that. So fundamental theorem of calculus. So let me remind you of what this means. The fundamental theorem of calculus in one dimension says that if you do an integral of the derivative of a function, what you're going to get if you take the x values, say from value A up to value B, what this is the value of the function at B, the upper bound, minus the value of the function at A. This is a fundamental theorem of calculus in one dimension, you could say that an integral undoes a derivative, or something like that. I know this is super loose language, but in a sense, an integral undoes a derivative. Because an integral is known as the antiderivative. Right, that was how it was presented to me when I was in math classes. Anyways, so let me put it in two ways. You have E, but you want V, so that's one situation. And the other is you have V, but you want E. Yeah, so this one over here, we already did this. This is how we learned how to define potential. In particular, if you have E, what you can always calculate is the potential difference. For example, up here, you're not getting F. What you're getting is the difference in F at two different places. Or, alternatively, you could say, for example, this construction is interesting. So, what if you take the derivative of F and you integrate over X? What you'll get is F up to an arbitrary constant C. Right? So this is if you have an indefinite integral, and this is the definite integral version. So in this case, what you get is potential difference. So there is a potential difference that's given by taking the electric field, actually the opposite of the electric field, and walking along some sort of a path from A to B. So the bounds are sort of symbolized by some starting location in space. This is an integral along a line or a path. So you start at some place in space, some coordinate, three-dimensional coordinate for us in physics, to some final three-dimensional coordinate. Yeah, so if you have E, here it is, and you want V, what this gives you actually is delta V. So this is, you could say, is the definition of the potential difference. So involves having to do an integral along a path. So you have to figure out how to parameterize your path. So parameterize a path for the integration. So yeah, so this is this idea. All right, so then over here though, what if you want to go backwards? In this case, to go sort of forwards, you start with E and you do an integral to get delta V. So it must be that we want to go backwards here. So instead, we take derivatives. So this, you take an integral, and now we're going to take derivatives. So it turns out like this. So you have V. What does this mean? It means that you have a function of space. That is, you know how V varies. So it's about whether or not you know how V varies in X, Y, and Z. So yeah, so once you have this, you can go and immediately write down the electric field vector, but it's actually given in components. So for example, the X component of the electric field vector, right? So this is EX I hat plus EY j hat plus EZ k hat, where EX, EY, and EZ are also possibly functions of space themselves. So Ex is a function of x, y, and z. So this is in general a function of all three coordinates, even though it is just the x component of the electric field. The x component of the field vector can vary through all three coordinates. And this is given by the negative of what's called the partial derivative of the function v, which you have the functional form of, by x. So this is a partial derivative. So partial derivatives are interesting. The idea is it's just like the normal derivative, except for you imagine holding the other variables completely still. So this kind of derivative is asking you to only imagine a variation in x where y and z have no variation at all. It's sort of the simplest thing that you might think is a derivative in multiple dimensions. So this is e sub x, e sub y, which is also in general a function of x, y, and z, is just minus dv by dy. And then ez is negative dv by dz instead. There is a word called gradient. And the idea is we are saying that the electric field is a vector equal to minus the gradient of the potential. So this is an upside down delta. This is not the same as this thing over here. This is referred to as del. So what the gradient is an operation. And in Cartesian coordinates, x, y, z, it just looks like I hat, partial derivative with respect to x, plus j hat, partial derivative with respect to, y, plus k hat, partial with respect to z, like this. And so you can kind of see how this works. This gradient acts on v, and then we tack on an extra minus sign. That's not part of the gradient. The gradient's all pluses. But we put on this minus sign, and that minus sign, actually, these are the same minus sign right here. So it's the fundamental theorem of calculus with a minus sign. Is the relationship between the scalar potential and the electric field. And it has to do with the fundamental theorem of calculus, but in 3 dimensions. We could say this is the fundamental theorem of calculus. FTC. Right. So so that's all well and good. So this is what it is, but it's honestly it's not that useful unless you figure out how to use it. Okay, so not useful until you see how to use it. So what we need to do is explore and maybe think of some thought experiments. So early on in your education, this is kind of a tough thing for you to do, but you should, as much as you can possibly do it, you should be doing this. You should just mess around. The only way that you can explore wrong or do thought experiments wrong is if you misuse your mathematics or you misuse your physics. As long as you don't misuse the math and misuse the physics, the limitations on you exploring and having thought experiments simply is your own inspiration. So the way you get to know anything is by messing around in it, within it, and figuring out how it works. Okay, so that being said, so let's explore this. Let's explore when let's explore the situation where you have the electric field, but you want potential. So let's imagine. Let's do this. Here is, so the sense in which I'm going to say we have electric field is by saying that I know how the field line diagram looks. So let me just sort of fake a field line diagram, right? So some of the rules are the field lines cannot cross, right? But other than that, and there's also actually, honestly, Gauss's law is a field line diagram rule, but I'm just going to draw field lines that don't cross. So they're doing a field line looking thing, and it would be difficult to figure out precisely what charge distribution would do this, but the truth is you know that multiple different charge distributions can have the same electric field line diagram in various regions of space. So a field line diagram doesn't impose you or restrict you to one charge distribution, but it does go the other way. One charge distribution does restrict you to one field line diagram. There's only one. That's the answer. But anyways, let's pretend we have a field line diagram, and let's pretend that I want to go from, say, here. So this is position A, right? Earlier, if we want to do this, we imagine a path from A to B. And I'm going to make sure to do a couple of things. I'm going to make sure that this path crosses a field line perpendicular. It crosses a field line sort of like not quite perpendicular or with the field line. And then I'm going to make this thing go along the field line and then cross it perpendicular again, just because whatever, it doesn't matter. It's my thought experiment, so I get to do what I want. I'm inspired because I want to teach you something. You might not be inspired, but you can draw any curve you want. But here, I'd like to point out that the crossing, so this path is directed. We start at A and go to B, right? So the idea is delta V, which is VB minus VA, is the integral starting at the coordinate A, whatever XYZA is, finishing at the coordinate B. But you have to figure out how to parameterize your path with these little ds vectors that are going to walk us along the path, get us from A all the way to B. And we're going to think about, oops, with a minus sign, the electric field, which is represented by the field line diagram, as we walk along the path. So I'd like you to see that the red path and this electric field line at this location right there is a situation of perpendicular. This one right here is neither perpendicular nor is it along the field line. So let me just put a question mark there for a second. So there's a little question mark. But over here, this is when the path direction is actually parallel, right? This means parallel. This up here means perpendicular. And then here again it's perpendicular. Okay, so this is it's neither perpendicular nor parallel. So actually it's a mix. So up here, let's call this an intermediate location. Let's call this, right, so on the way from A to B, we're going to go through all these various coordinates, and our little ds vector is going to take us to the next coordinate, next coordinate, next coordinate, next coordinate, next coordinate. And at some point, the ds vector that we're looking at when we are here is a little ds vector that points that way, right? Which is crossing the field line perpendicular. Right here, the little ds vector is moving, or is that direction, right? It's along the path. Right here, the little ds vector is actually parallel to the field line. And again, the ds vector down here is perpendicular, right? So let's call this position, let's call it P1. This is the position P2. I mean, there's an infinite number of coordinate positions along the path in between P1 and P2, but you can imagine, like, I could split this integral and go A to P1, then P1 to P2, then P2 to P3, right? They're just positions along the curve. And then here's a P4. Okay, so at P1, the electric field value is perpendicular to the ds vector. The little ds vector is here. That's the ds vector. The electric field's value is this way, indicated by the field line, the field line's direction. And the density of field lines speaks to the strength of the electric field. But I don't care about the strength right now. I'm worried more about its direction. Direction is that way. So at P1, if you look at what happens to E dot ds, right? This is, forgive me for doing this, this integral that I'm adding up from A to B is an integral of small contributions to changing the potential, right? And if I finish the entire path, I'll have added up all the dv's and arrived at the total delta v. So there is a small contribution to the change in the potential at P1, and this, if the vectors are perpendicular, is 0, because the dot product between perpendicular vectors is 0 at P2. So here's P2. So at P2, it's a little bit more complicated because it's a mixed situation. But this is kind of a cool way to do this. Think about the ds vector as being actually the sum of two different vectors. So if I look at this vector, let me redraw it. So take this vector down here, it looks like this, and that's equal to a vector that points, oops, sorry. Let me just write it up here and then I'll try to explain it down there. So what I'm going to do is I'm going to say that the ds vector, this red arrow right here, is actually equal to a ds vector that's perpendicular to the electric field plus a ds vector that's parallel to the electric field. So the ds vector, if I just translate it, so this arrow I drew over here, I'm going to draw it right underneath. So this is an arrow that looks something like this. So the electric field is this way, so the ds that's parallel is actually anti-parallel. It's a little vector that points along the electric field line like this, and ds perpendicular is this piece that's perpendicular to the field line, so it's this thing here. And if I add these two vectors, what I get is the small actual vector along the path. And what I'm trying to get at is that dv is equal to minus e dot this combination of ds that's perpendicular to the electric field plus the ds piece that's parallel to the electric field. And we know that if the ds that's perpendicular, this one, we're talking about the perpendicular part, when you do the dot product between this vector and the thing that's perpendicular to it, it's just 0. So the only contribution to a change in the potential as I move across the field line right over here is given by ds parallel. That is, the dv accumulates only based on having directions in common with the electric field. So at P3, this is the situation where if I move along the field line, so it looks like ds is fully parallel with the electric field line, right? So here is the ds vector. It's this little arrow pointing towards the right, and the electric field also points towards the right. So they are parallel. So ds is parallel with E, so that delta, the small contribution to the potential change equals minus E dot ds. It's equal to, well, actually, let me say that since E is actually in the same direction as ds, the dot product is a positive number, right? This is positive, but there's this minus sign. So let me just say that at P3, dv actually, it shrinks. So this is a situation where we lose a little bit of potential difference. So as I'm accumulating delta V from A all the way to B, sometimes I'm going to be losing potential. Sometimes the potential is not going to change at all. That's when I move perpendicular to the field line. And most of the time, honestly, for a generic field path through a generic set of field lines, you're going to have mixtures. You're neither going to be purely perpendicular nor purely parallel. So, but the idea is it only ever picks up the parallel pieces. Yeah. So in this case, actually, if you look, since this is an if you look at this, this dv is actually going to end up positive in this case at P2. At P2, the potential will accumulate positively. At P3, because we're running with the field line, we're going to lose potential. So we must gain potential if we go against field lines, and you lose potential if you move in the direction of field lines. So as a summary, you gain a potential difference if you move against a field line direction. I'm going to put anti-parallel, ds is anti-parallel to E, right? So you gain potential difference if you move against a field line direction. Potential difference does not change. That is, the contribution to the potential difference is equal to 0 if ds is perpendicular to the electric field, right? So anti-parallel was actually, in this case, this parallel piece actually points backwards, right? This is at P2. Here's P2, point number 2. The electric field points this way, and the component of ds that points along that direction actually points backwards to it. So these are anti-parallel. There's 180 degrees between their directions. So when you calculate the dot product of anti-parallel vectors is negative, but the definition has another negative sign, so ultimately it's a positive change. Yeah. This right here is an important point. Actually, both are important points, but for the purposes of a diagram later, actually, the diagram is actually important for both points, actually. So let me say that we are going to be talking about equipotential surfaces, and the surface shapes will be dictated by perpendicular to the field lines, but the way that the potential increases or decreases is going to be given to us based on whether or not we're walking up against the electric field lines, or are we walking outwards with the field line direction. So please keep this in mind when I talk about equipotential surfaces. Okay, so let me move on. So let's explore have V but want E. Okay, so I have two examples. So point charge Q at the origin, right? So I showed you that you could define a potential that's equal to Q over 4 pi epsilon naught times R, right? Where R is the distance away from the charge Q. So if I put the charge Q at the origin, so here is the x-axis, y-axis, z-axis, so I'll put Q right here, then a distance R away. So let me draw a point P, and if I drop an altitude on P, it goes to there. So let's say that that is the y coordinate. This is the x coordinate, and you have to be sort of careful. It's hard to draw. This is the z coordinate. Can you see I drew a little solid rectangle almost in this dashed line? So that's how I'm going to sort of depict the position P. And that position P is a 3D Pythagorean Theorem distance R away from the charge Q. Q is at the origin, right? So R is just simply x squared plus y squared plus z squared, of course. That's the Pythagorean Theorem in 3D. So this is the R that fits right there. So I have a potential as a function of x, y, z that's equal to Q over 4 pi epsilon naught. It's epsilon naught. And then 1 over x squared plus y squared plus z squared to raised to the 1/2. So if I want to know what is the electric field in the x direction, right, it's equal to minus dv by dx. So this is equal to, here's a minus sign, and then I just got to take dv by dx. So q over 4 pi epsilon naught, those are all constants. So what I need to do is apply d by dx, this partial derivative, on this 1 over r. So it looks like the following. This is, let me not skip any steps. So this is x squared plus y squared plus z squared, whoops, raised to the negative 1/2 power. So you can see how this is going to go. This negative 1/2 comes down, and there are now two minus signs. So let me put them all in. So minus q over 4 pi epsilon naught. You get a factor of negative 1/2, right? And then you multiply by this thing reduced by a power. So this will be x squared plus y squared plus z squared raised to the negative 3/2 power. And then you multiply by the derivative of the inside. So that's the chain rule. So that's 2x, like this. And so you can see that this 2 cancels with the factor of a half, and this minus cancels with that minus. And you're left over with, check this out, it's q over 4 pi epsilon naught. I'm going to do something funny. So you see this x squared plus y squared plus z squared to the negative 3 halves. That is, so let me, I won't skip any steps. So this is x squared plus y squared plus z squared to the 3 halves power on the bottom. And let me just do something interesting. So this is q over 4 pi epsilon naught x squared plus y squared plus z squared. I'm going to put it to the first power. So 3 halves is 1 plus a half. So I need to, so I'm going to put that multiply by x over x squared plus y squared plus z squared raised to the 1/2 power. So this is 2 halves plus 1/2 is all 3 halves, right? But I've got this extra factor of x. So let me put that in square brackets off to the side. If you go and you do EY, you will get, whoops, everything here except for, instead of getting 2x, when you do EY, you're just going to get 2y instead. So everything is the same except for what pops out is a y. So this will be q over 4 pi epsilon naught. This thing right here is actually r squared, right? If you remember, r is the square root. So if I don't have a square root, I got to the first power. That means that this is r squared. And then this is y over r here. And ez is q over 4 pi epsilon naught r squared. And then this, for z, the z comes out instead. The same factor of 2 killing the half. The minus sign's also doing exactly the same thing. So if I summarize, I get q over 4 pi epsilon naught r squared x over r. Okay, so let me now take all of this information and write down the electric field vector. It is a function of x, y, and z, and it's equal to, remember it's I hat ex plus j hat ey plus k hat ez. So if I write all this out, I get, I'll cut to the chase. Hopefully you can follow this along yourself. So it's q over 4 pi epsilon naught r squared. That's, everything's got that preamble, prefactor in common. It's also got x I hat plus y j hat plus z k hat, all divided by r, right? And this is q over 4 pi epsilon naught r squared, r hat. This right here is r hat. This is Coulomb's law. Cool. Another example is actually, yeah. Well, actually, I don't think I need another example. You kind of see how I had to be really careful. You know what? Yeah, I think an example is important. So let's do circular ring of charge. So we'll say it's a uniform linear charge density lambda. Okay, so what we're going to do is let's get V first, then imagine getting E from V. Okay, so let's get V first. So draw a picture. So let's say that our ring lays in the x y plane. So this is the z-axis is up here. And here is a picture of the ring. And let's imagine, so this is my charged ring, ring of charge, uniform density, let's say radius capital R. All right, so let's take a small arc length ds. So ds equals, so it's at the radial distance r, and we imagine sweeping with angle phi. So we are sweeping an angle d phi, like that. And phi is going to range from 0 all the way around to 2 pi, because that's how much of a ring we have. We have the entire ring. So in the small angle d phi, there is an arc length at the radius r of r times d phi. So d phi is in radians. And the amount of charge that sits in that little arc length is equal to lambda times the arc length ds, which is lambda r d phi. So this is how I'll understand the little point charge. And if I look, I'm going to find on the z-axis, let's say that this coordinate right here is 0, 0, z, right? It's actually on the axis. So 0, 0, z. Let's get v along the z-axis. So this will strictly only be a function of z, because we're going to only ask along the axis. So let's get that first. Let's get v of z first. Okay, so there is a small contribution to the potential because of a charge dq. There's a 4 pi epsilon naught that always comes along for the ride, times a distance r, right? So the cool thing about scalar potentials is it's only ever scalar, and the distance r is just the scalar distance r. And in this picture right here, for this particular element, the distance is the red line, a Pythagorean Theorem line. The bottom of that triangle is capital R, and this edge length of the triangle is z. So r is always r squared plus z squared with a square root. Just do the Pythagorean theorem. Okay, so there's dv. And if I want to know what is the total v at z, I just need to integrate all the way around the circle, right? That's how the dummy variable ranges. It goes from 0 to 2 pi. And dq is lambda r d phi. And divide by 4 pi epsilon 0, and then r squared plus z squared to the 1/2 power. So what's cool about this is super simple with respect to the potential. Nothing in here depends on phi except for d phi. So it's just the clock hand. So it'll be lambda r over 4 pi epsilon naught r squared plus z squared to the 1/2 power. And then you integrate from 0 to 2 pi of d phi. Cool. So, wait, am I doing everything right? I think so. So then, yeah, I guess so. So then, if you do the integral, this becomes, 2 pi lambda r over 4 pi epsilon 0 r squared plus z squared to the 1/2 power. And I'm going to go ahead and divide the 2 pi and the 4 pi, so there's a 2 left over, so lambda r over twice epsilon naught r squared plus z squared to the 1/2 power. So how can I use this? Well, I can ask questions. Well, what's the electric field? So here is the hard part of this. The electric field that you can get is only restricted to staying on the z-axis. And the reason is because we didn't put into any of this work any information about x or y. So we can only get the electric field for 0, 0, z, where z is generic. But be really careful. So what I mean by this is, so check this out. So z is the easiest one. If you take the derivative with respect to z, you'll just get, so e sub z is minus partial with respect to z of the potential. So I know how z varies. So it's down here with the square root of z squared business. So if you do the thing quickly, so I guess it goes lambda r over twice epsilon naught. All right, and then you'll get r squared plus z squared to the 3/2. You'll get a minus 1/2 multiplication on the front from the thing, and then you'll get multiplied by twice z, like this. All right, so some cancellations again. Oh crap, and then there's this other minus sign. So man, this is really becoming sloppy all of a sudden, but this minus sign is from the original definition. That minus sign is because I took the derivative and I had of a rational function where the bottom had the variable in it. So there's a minus sign that comes up because of that exponent. Anyways, I bet you can follow, or I hope you can. So this minus and that minus knock each other out. This 2 and this half knock each other out. And so Ez equals, I guess it's a lambda r z over twice epsilon naught yeah, r squared plus z squared to the 3/2 on the bottom. Like this. So you might go and compare this to, so compare to earlier video or book. This tends to be a typical example when you're learning to calculate the electric field. What you learn in this case is that you can calculate the electric field along the axis. So along the axis, the axis is a symmetric axis. Axis is axis of symmetry. So it's in the charge distribution. And what this means is that we expect, because of the symmetry, that there are no x and y components, because in a sense the symmetry makes the choice of x and y arbitrary. So if the choice of x and y is genuinely arbitrary, there's no physical thing you can determine in a choice of the arbitrary choice. So that means that that the electric field can only be 0 in those directions. So if I go and I check, well, how about Ex? It's minus dv by dx. If you look at v, this is v right here. It's only got an explicit dependence on z. So when you take the derivative, it's just 0. If you go and you check Ey, similarly, you'll get 0, because when you take the derivative with respect to y. But this is the case only on the axis. Off-axis is more difficult. So let's explore that problem really quick. So here is an XYZ coordinate system again. So y-axis, x-axis, z-axis, and here's our charged ring. May as well just put it at the coordinate system center like this. But now let's imagine asking about this position here. So that's a point whose y value is here, whose x value is here, and whose z value is somewhere up there, right? So the z value is, you have to go this way to the z value. So this is the z value up there. Okay, so what makes this really hard is when you imagine looking at that little piece of charge, dq, when you go around and add up the total potential at x, y, and z, so the problem is dv, the small contribution, is still a dq over 4 pi epsilon naught, but there's the r, and the r is actually from the charge element to the place in question. And in this case, different charge elements will have different r values. So this is r when we're talking over here, and this is a different r when we're talking about charge elements on the back side. So this is a complicated function of x, y, and z, and this leads to a difficult integral. It's not hard to set up the integral, it's actually just difficult to do the integral. And so the difficulty in doing the integral, though, is going to give you some complicated function of x, y, and z, right? So v is a complicated function of x, y, and z. And we might say that it's very complicated. So when you go and you take minus dv by dx, for example, to get the x component of the electric field, it's a complicated process, right? You're going to take this super complicated xyz function and then take a partial derivative with respect to x in it and multiply by minus 1, and then you can write out e sub x. It's still going to work. It's just maybe not going to be the easiest way to do this. It might be easier, honestly, just to go ahead and calculate the electric field directly. It's not that the potential is going to help you shortcut the process or something. Okay. The next topic to talk about is it's a diagrammatic topic called equipotential surfaces. It's really about pictures. So equipotential surfaces. Equa is equals, right? So these are all the potentials are equal, or equal potential surfaces. So let me start by describing not equipotential surfaces, but just the idea of a surface, just a surface. A surface is a collection of points or coordinates that indicate a two-dimensional space. So surfaces are 2D is what we're talking about. An example is the surface of a sphere of radius r, and I don't mean a volume sphere, I mean just the top surface, the outer coating. Another one is a surface with a constant value of x. So if I imagine three-dimensional space, there is a plane, a flat plane of a whole bunch of coordinates where every different coordinate on the flat plane has different values of y and z. So this is kind of like a yz coordinate system in here. So yz. So this is a sort of a yz plane but every position has the same x naught. So this is a plane that's parallel to the yz plane, except for where the x value of all the coordinates is some particular x naught. These are just surfaces. You use surface, yes, these are just surfaces. They're a mathematical idea. So with that in mind, let's study a point charge. Right? So here's a point charge. So if I think about the potential of a point charge, is only dependent on the distance away from the point charge. So let's say the point charge is capital Q. 4 pi epsilon naught comes along, divide by the distance from the charge that we're asking for the potential. So if this is a, say, x, y coordinate system, then if I agree to only ever stay the same distance away, then all of these locations on this circle here have the same potential. This is an equipotential ring, right? But it's not a surface. The way we'll get the equipotential surface is if we also include the third direction and imagine all of the other ways that we can just stay a certain distance away from the charge. And so if I imagine putting the z direction, which is out of the page, if x is to the right and y is up, then the z direction is out of the page. And now I can talk about a sphere of radius r. So if I imagine points on the sphere of radius r, all of these positions have the same potential. All the positions on an equipotential surface have the same potential. What this means is, like, let's say that there's a position A and position B are points from the same equipotential surface. Then if I tried to calculate delta V, which is the integral from point A up to point B of the electric field times little ds vectors, or dotted with ds vectors, this will only ever give 0 if PA and PB are on the same equipotential surface. So let's say that PA is here on the surface of radius r, and point B is over here. And I could stay on the surface, take a great circle from A to B, or I could come off the surface as long as I get back onto the surface for B. And either one of these paths, I could take the one that stays on the equipotential surface, or I can come off the surface and go back on, and I'll still only add up to 0. Okay, so continuing with this example of a point charge. So here's a point charge Q, and let's say that this is the equipotential surface at the radius R, for example, right? So this is a two-dimensional depiction. It's really three-dimensional. But this is at R. And so this potential surface is V, all of these positions on the surface have the same potential, equipotential surface V, and V is Q over 4 pi epsilon naught R, right, where R is that radial distance. If I imagine a surface at twice R, then that surface is also a sphere, which looks like a circle when I draw it in two dimensions. And this thing has radius 2r, and the potential at this equipotential surface is V over 2. And the reason, if this is called V, then this will be half as much, V over 2 at twice the radius, right? So this is the potential at R, and the potential at 2r equals Q over 4 pi epsilon naught 2 times R, which is equal to 1/2 of Q over 4 pi epsilon naught times R, and this is equal to 1/2 of the potential at R, which we're calling V. So that's V over 2, and you can see that if I go out to 3R, this equipotential surface is V over 3. It's this potential here, but a third of it if it's a surface of radius 3r. And then also, check this out, you can go inside and imagine an equipotential surface of radius r over 2, and the potential here is going to be 2 times V. So these are all different equipotential surfaces. And if I was to go calculate delta V, say from here, this is position A, and let's say that this is position B, and I'm going to follow a crazy path all the way to B. Then when I calculate this, this will only be the potential at B minus the potential at A, and the potential at B is twice V, and the potential at A is V over 3. So that's like 6V over 3, so 5V over 3. For example, these are equipotential surfaces for a point charge. One last example is, what if we do this might be cool. I'm going to draw a picture. So this is, say, an x-axis. This is a z-axis. And this axis, I'm going to fake you out, is not the y-axis. This instead is v as a function of x, comma, 0, comma, z. That is, the y value is always equal to 0. And so we are looking at the potential for coordinates whose y value is 0 and whose x and z values aren't determined. It's going to be drawn. And let's say on the x-axis we put a positive charge and a negative charge. So this is a charge negative q, and this is a charge positive q. And this is a electric dipole. And I'm going to imagine what the equipotential surfaces have to look like. So this is pretty cool. If you go, and so y equals to 0 everywhere, right? So this is only a depiction of the potential for coordinates whose y value is 0. That's kind of like a weird thing to say, but that is the case here. So what you'll find, and this is neat, along the x-axis, you're going to get a potential function that it gets very high as you approach the positive sign, coming from the large values on the x-axis. But then on the other side, it's going to come down. It's going to be like a sharp peaked thing. But the way it's got to go is it's got to, right, potentials around negative charges are negative. So if I'm closer to the minus sign than the positive sign, then the potential is going to drop down. And on the other side, I'm going to come up to 0 as I go out to x goes negative infinity. So this turns out to just be the answer. So this right here is an asymptote for the potential for z equals to 0, actually, like this. So the potential function looks like this. And on the other side, it comes down to the origin, crosses through, and runs up against the asymptote that runs through the position of the negative q charge. And then on the other side, it just looks like this. And in the z direction, what you find is that these are just basically circles. They're kind of like circles. They're not exactly like circles. They have a pretty interesting shape. They just go around like this. And these indicate equipotentials. So the potential here has a different value than the potential there. The potential here is actually higher. This is a big value of V. This is an even bigger value of potential, and this is a somewhat smaller. And then if you go and you imagine drawing the same cycles down here, this is a negative value of V, and then a more negative, more negative. So these are circles in the xz direction, but these are only slices through y equals to 0. So these aren't really the picture of the full equipotential surfaces. This is just, this is like a slice. It's a projection onto y equals to 0 in a sense. Yeah, so these are equipotentials. All right, so last thing I'm going to say is here is a point charge, and what I'm drawing are the field lines of the point charge. So this is the electric field. And the equipotentials they are always surfaces that are perpendicular to the field lines. So equipotential surfaces are perpendicular to field lines. So this is a, like, as you get closer to a positive charge, here's a positive charge, as you get closer and closer, the potential grows. And it grows to infinity if you stand right on top of the charge. For negative charges, as you get closer and closer, the potential goes to negative infinity instead of positive infinity. So that's how the potential works nearby plus and minus. So this equipotential surface is, say, for a high value of potential, and this equipotential surface here is for a lower value of potential, right? So you can imagine that if this axis towards you is the potential axis or the voltage axis, then this is this cone rising up towards you like this, as your eyeballs up above. So equipotential surfaces are perpendicular to field lines. This dipole, let's draw its equipotential surfaces. So here is a plus and a minus, and you may remember, but the field lines for a dipole looks like this. So I'm going to try to draw as symmetric as I can. So this is the outbound field lines connecting around to there, and there's another one over here. I guess I can draw almost all of it. Inbound, whoops, and this is outbound. Okay, so I need to figure out how to draw equipotential surfaces. So here is a line. Do you see this? This indicates a surface that is perpendicular to all the field lines. Because of the symmetry, the way the field line is going to cross this central up-down axis is perpendicular everywhere. So this is an equipotential surface, and it's kind of strange because what it's going to do is it's actually two equipotential surfaces that split apart at infinity and come around in a weird way. Yeah, so is that true? I might have just said something wrong. Anyhow, check this out. Here's another equipotential surface. So all I got to do is imagine connecting these dots such that they're all perpendicular to the field lines, right? And at some point, this is going to also cross this thing. So let me try to force it. So it's supposed to be a right angle there, and it goes out. And then let me draw some more. So here is another equipotential surface. Perpendicular, perpendicular. Okay, so I'd like you to look. So what I'm referencing, this dipole diagram, I want you to pay attention to the cycles that I would draw over here. They are here. So this cycle that I drew is like this big one. And if I draw this one instead, that one is, say, this smaller one. And if I draw an even deeper one, then what I'm talking about is, say, this one instead. So this is V very low. This is like a very negative value of V. And this is sort of V sort of kind of low. And then if I go over to the positive side, then this is, for example, a very high potential surface, V very high. And then here is an equipotential surface, say, that is V just sort of high. And so the middle value is this line right here. So this is mounding up, and this is more like a deep hole, right? So it's just another point of view. It's sort of the top-down point of view of this drawing, except for I drew them backwards so that I could crease the page and show you. Yeah, okay.